Hey everyone, it's your perfectly normal math teacher, Mr. Boyden, back at it again today. And why am I normal? Well, I guess actually I'm abnormal because today we're going to be talking about normal distribution, and I'll give an example of how I'm actually a little bit abnormal here in just a minute. To introduce normal distribution, I want to tell you a really short story. About 3 or 4 years ago, I was feeling sick and was having some problems, so I went into a walk-in clinic, and they were not sure what was wrong with me. So what does any good medical professional do when they're not sure? They're going to run some tests. And so in my case, they ran some blood work, and I received a copy in an email that said, they test for 38 or 50 different things, and you get to see what the normal range is, and you get to see if you're inside the normal range. And almost every time I've ever had a blood test in my life, everything comes back fine, and it says that I'm normal, and I go, okay, normal's good, so I'm nice and safe. But on this particular occasion, there was one thing they tested for where in big red letters it said that I was abnormal. And that freaked me out a lot. You see an abnormal blood test and you go, oh my gosh, am I dying? Is there something wrong with me? Oh my gosh. So I called the clinic to ask them what was going on, and they said, we're sorry, Mr. Boyden, we actually cannot discuss that with you, but we would encourage you to make an appointment with your primary care provider so they can inform you of what this is. And so that freaked me out even more. Okay, I've got an abnormal blood test, and they won't tell me what it means. Okay, so that really means I'm dying. I'm really toast, right? So I go into the doctor, my normal doctor that I go to, and he sits me down, and I ask, okay, I've been really freaked out. Can you just tell me, am I dying? And he says, no. You're not dying. I say, how do you know that? It says I'm abnormal. And he said, right. You're a math teacher. You should know what normal means. You know what normal means? And I said, well, I can think of things that normal means, but I'm not sure. So here's what he explained to me. He said, Mr. Boyden, this test, the normal range goes from 2 to 16. And you tested at 16.1. He said, I don't think you're dying. And here's why I don't think you're dying. Because last year, I did this same test when we had your physical exam, and you got 15.9. And the year before that, you got 16.0. And the year before that, you got 15.9. I said, so look, in 4 years, this level in your blood has hardly changed at all. So why would we think, since it's hardly changed, that now something's wrong? I said, well, but I'm sick. He said, but do you feel sick anymore? That was a couple of weeks ago. I said, no, I feel fine now. He said, see, there's nothing wrong. So then I grilled him a little bit more. I said, well, wait a minute. If I'm perfectly healthy, then how can this blood test say that I'm abnormal? I said, okay, well, let's go back to that range that was given, 2 to 16. He said, here's what we do. We test like 1 million people's blood. We take a huge number of data points. And what we find when we do that, and we align those data, is we find that they are normally distributed. And so guys, here's what normally distributed means. Okay, it means that it falls along what we normally call a bell curve. Where in the middle, you have the mean, that's mu. So the mean value, or the average, and then it's spread out based on sigma. And if you recall, sigma squared is the variance, but sigma is the standard deviation, which describes how spread out the data are. Standard deviation. And he said, and what we find is that when we do blood tests, people's ranges tend to fall in here. And so there's some mean, and on yours, the low end was 2, and the high end was 16. And where we assign those values is 2 standard deviations away from the mean. And so you are just a little bit higher than 2 standard deviations away from the mean. He said, so that means you're abnormal. It doesn't mean you're unhealthy. Some people have high levels, some people have low levels. Sometimes that can be a sign of something wrong. But he said, with this particular test, and in your particular case, there's no problem. He said, there's nothing for you to worry about. And I felt a little funny about that, because still, anytime you're labeled as abnormal, you kind of scratch your head a little bit and wonder what's going on. But he said, you know what, Mr. Boyden? You're abnormal in another way that I can tell just by looking at you. And it's like, oh, thanks, doc. Really appreciate that. He said, no. Look, you're 6 feet 3 inches tall. And that is going to be on the high end of the height spectrum. He said, so if we draw a bell curve, and the average height for a male is something like 5'10", and then we go 6 feet, and then we go 6'2", and you got to go the same the other way. Remember, this is the median and the mean right there in the middle, and please excuse my level of drawing accuracy. I'm still not very good with this pad that I'm writing on. So then there's 5'8" and 5'6". He said the normal range is something like this. And you, at 6'3", you fall outside the normal range. He said, so you're abnormal in more ways than one. He said, do you think you're dying because you're 6'3"? I said, well, no, okay, probably not. That's probably not reasonable. And he said, see, so just because you're abnormal doesn't mean that there's a problem. Instead, abnormal can be just fine, and in your case, it's not a problem at all. So, guys, that's kind of a cool thing to think about even for life. It's like you're abnormal, but that's cool. It's a good thing to be abnormal in some ways and in some things. So, kind of a new way to think about the word normal. So what do we know so far? We know that a normal distribution is symmetrical and it's bell-shaped, and sometimes when we grab data from some event, it happens to follow a normal distribution. Heights of people tend to be normally distributed. Most people are pretty close to the average. Some people are really short, some people are really tall. Okay. Blood tests are that way. I actually did a little more digging on this. I went to the Mayo Clinic, their website, and I wanted to see if I could find any more information about this. And they, on their source, they actually call it a normal. And I found complete blood count was one. That's not the test that I had an issue with. But normal complete blood count, and they have a normal range. So what that is they're taking a whole bunch of data points, they're graphing them, finding that they're normally distributed where, look at this, 68.2% of the data fall within 1 standard deviation of the mean, and 95 fall within 2%, or within 2 standard deviations of the mean, excuse me. And then as we get farther and farther away from the mean, there's less data points or less people that fall into that range. And so that's actually how they interpret blood tests. Now that's why we need doctors and nurses and PAs to help us understand what they mean, because for me, I assumed I was dying and getting ready to write my will, but no, they were able to use their training to understand what it means a lot more than I do. Hemoglobin, that's another one that's normally distributed, and so we have that range. If you're outside the range, does it mean anything bad? I don't know. I'm not a doctor or a nurse or a PA, so I can't tell you. But one thing that I found really interesting on the Mayo Clinic website is they exclaim that this is not a definitive test. They're talking about blood work in general. A complete blood count is typically not a definitive test. Depending on the reason your doctor recommended it, the results outside the normal range may or may not require a follow-up. So they're saying you might not even need to follow up. It might just be fine. The doctor may need to look at the results of that along with other blood tests, or other tests may be necessary. For example, if you're otherwise healthy, like I was and like I think that I am, and have no signs or symptoms of illness, which is where I was when I went to the doctor finally, results slightly outside the normal range may not be a cause for concern, and follow-up may not be needed. So that was very, very interesting to me when I learned that. I was actually really surprised, but then when he explained it to me in terms of statistics, it made a lot more sense to me. So what we're going to do today, we're going to see some applications of the normal distribution, and we're going to see how it's used, because this is something that's always on the IB exam. Okay, so a couple things to look at before we continue. First one is, I want to bring box and whisker plots back. And I want to ask you a couple questions. Do you remember what IQR stands for? We're kind of reviewing as we go, right? IQR stood for interquartile range. Q1 is quartile 1, quartile 3. Our median says that half the data points are on the left, half are on the right. And what percentage of the data points are in this box right here? I hope you remember that that's 25%. 25% of the data points fall in this range, 25% fall in this range, and 25% fall in this range. Now, a minute ago, I used the number 68.2 to describe this region right here, but notice that was from 1 standard deviation to the left and 1 standard deviation to the right. That's the area that is 68.2%. The other thing I want you to notice right here is notice where the shading's at. See how this is shaded? What does that remind you of that we've learned about this year? Because it's shaded under the curve. So y'all, I want you to see that this is an integral, and this is why I'm saving this to teach until kind of the end of our calculus, because if we understand that this is an integral and we use our language from integrals, it's going to be really easy to understand these. Okay, final thing on this page, standard normal distribution. This will sometimes come up in questions. All that means is they're telling you this right here. Now, do you remember what that number on the left meant? That was the mean, and we write mu for that, and this number on the right is our variance, or in this case, since it's 1, it's our variance and standard deviation are the same. Okay, so be looking out for that. A lot of times they're not going to tell you this. They're going to say standard normal, and that's going to come up again in just a minute. Okay, so now let's bring in a calculator so we can see how this works. We're going to use the calculator to verify that, in fact, 68.2% of the data are within 1 standard deviation of the mean. So follow along with my keystrokes on the calculator over here. What I'm going to do is on my Inspire, I'm going to go into the calculate menu, and once I'm there, everything good happens in the menu, recall. So if you go menu, where do you think we're going to find normal distribution? There's actually 2 places. We can find it both in probability and statistics. I like to go to probability because see how this is menu item number 5, and then in here distributions again is menu item number 5. So there's actually a shortcut to this. So if you hit menu 5, 5, it'll take you right to your distributions. And I've clicked the wrong one, so I'm going to have to redo that. And so the one that we want is we want normal CDF, okay? And the reason we want that is that's going to ask us for lower and upper bounds. That's going to be important because if we choose PDF, it's going to ask us for a single value. That's going to give us a Y value. The Y values mean a probability, but it's kind of misleading. So it wouldn't really be the probability of that one point. It would be what the function says the probability would be. What's most meaningful is to do an integral. And we can see that on the calculator right now because you've got lower bound and upper bound. So back to our question that we were asked. We want to verify that 68.2% of the data are within one standard deviation. So let's work on our bounds. Okay, lower bound, since it's a standard normal curve, that means the mean is actually 0. And the standard deviation is 1, so that's 1, 2, 3, -1, -2, -3. We're going to verify that, so our bounds are -1 and 1. We're shading in between those. So I'm going to come back over to my calculator, -1, 1, and we're going to use 0 and 1 because we're doing a standard normal distribution. Let's hit enter and see what we get. I get 0.682. I told you 68.2%. It looks like it actually rounds to 0.683. But that's what we mean when we say verify. So I guess, okay, that should be a 3. But that's how we're going to verify that in the calculator. Now let's do some visual practice, and I'll walk you through how to do this. So we're going to use our GDC, which is our graphic display calculator. We're told that it's standard normal distribution, and we're going to find each of these shaded areas. One thing I want to bring up to you before we do that is, what if the entire area was shaded? So for example, what if everything under this curve was shaded? Do you know what that would sum up to? Keep in mind that this shaded area represents a probability. And so if you add up all the probabilities in any given context, what will they always sum to? They'll always sum to 1, right? So like coin flip, heads or tails, 50-50, that adds up to 100%, which is 1. And that's why this is a number that's smaller than 1. Okay, it's always going to be between 0 and 1. So let's keep that in mind as we go through this. Okay, let's go to our first one. We're going to do A. So I'm going to go back into the menu, 5, 5, normal CDF. And let's talk about what this business is. That -9e999, that's scientific notation. It means 9 times 10 to the 999th power. And what you need to know is that is a massively big number, and it's down there on the negative end of the number line. And so what that's doing is the calculator doesn't know what infinity is, but it knows that if it picks a massive number, then that's just as good as infinity for the purposes of this approximation. So that's saying negative infinity. Looking at A, this goes to the left forever, right? So the normal distribution curve, it technically has the x-axis as an asymptote. These go on forever. And so that's why we're going to use negative infinity on the left side. It's unbounded. See how there's no bound over here? It's unbounded. So that's what we're going to use. Upper bound, it's 2.55. So let's plug in 2.55. And I get 0.994. Okay, there's my first answer. 0.994. Let's go to the next one. And I want to do this, actually, I want to do this all in the easiest way possible. So check this out. What I'm going to do is I'm going to hit up twice here to highlight that. Then if you hit the enter key, it'll bring it down so you can edit it. And why that's nice is now you don't need to go through all the menus. You can just type in exactly what you want. So what I'm going to do, I'm going to look for which of these questions, based on what I already have here, will be the easiest. And what I mean by that is I already have negative infinity here. Do you see which of these other examples will also require negative infinity as a lower bound? It's C, because look, it's unbounded on the left side. So all I have to do is change my upper bound to negative 1.5. And now I'm golden, and there it is. So 0.067. All right, so I don't have any more with a lower bound like that, so I'm going to have to actually do a little bit more work on this one. So, but all I'm going to do is I'm going to go back and edit my information in here. Let's do B right now. B starts, it looks like at negative 1.2. And it goes to the right forever. So this is a good time to show you how we're going to plug that into our calculator. So I got to delete my old upper bound. And what I'm going to do is I'm going to go 9, and this is the button we need right down here, y'all, that double E, because that's what the exponent is. If you hit this E, it's going to think you mean the number E. That's not what I want. I don't want the number E to the 999th. I want literally exponent of order of magnitude of 999. So I'm going to go 999. Now I'm all set up. I hit enter, and I get 0.88549. Yep, that rounds to 5. Wonderful. Make my decimal point a little more pronounced there. Okay, let's do D. And D and E are going to be very, very similar. Okay, so we're going to go back into here. We're going to go play with our bounds until we like them. So my upper bound on D is 1.23, Because I want you to think about bounds just like an integral. You see how that looks like an integral question, an area under a curve with bounds on the left and right? So 1.23, I'm going to go back, I'm going to put in 0.7 as my lower bound. Okay, and this would be a good place to talk. What if you flip your bounds? In the calculator that we're using right now, if you flip your bounds, it's going to reject your answer because it's going to think you're confused. It always wants your lower bound to be to the left or to be less than your upper bound. We know from calculus that if you flip your bounds on an integral, all it does is give you the opposite answer it would have had otherwise. And yes, this is actually doing integration. The calculator is doing integration to find these values, but they also recognize that in this context, you always need your bounds in order. So it'll reject it if you get that wrong. So if you get that error, like a domain error, that's probably why. Okay, so 0.13 on this one, 0.133 is how I'm going to round it. And then the last one, go back and change the bounds. Looks like 0.62 and negative 1.3. Oops. Yeah, nope, I'm good. Okay. 1.3. Even math teachers get confused for a minute sometimes. All right, so 0.636. Cool. So, because all this was for, the purpose of this was to just show you how the calculator works, okay? This is not necessarily a test type question. It's just to give you some familiarity with this TI Inspire. Let's look at an actual context of something that truly is given by a normal distribution. So every year, they scale the SAT scores. Notice your raw score and your scale score aren't the same. They're actually going to scale the scores on the SAT to make them a normal distribution. Now, this is from the old SAT where a perfect score was 2,400. And so they've changed it back down now to 1,600 again. In the old days, it was 1,600. Then when I was in school, they switched it to 2,400. Now they switched it back. So this is a little bit of an old visual because they changed it back very recently. But it'll still be useful for us to talk about it. So what we could do here is we could ask questions like, and I haven't put any questions, but we can kind of write any question we want. And that's kind of the purpose of statistics, is we could write something like, what percentage of students will score higher than let's say 2,000. Okay, so I'm going to look here. 2,000 appears to be right there. So what percentage of students would score higher than 2,000? Now let's relate that to what we did a minute ago. See how visually it looks very similar? So what we're going to do, we're going to pull our normal CDF down. I'm going to go back in and I'm going to edit these numbers. So I want it to be more than 2,000. And then my upper bound, realize that yes, a perfect score is 2,400. However, your calculator doesn't know that context. And so if you put 2,400, you're going to get the wrong answer. Your calculator thinks this curve goes forever. And higher than 2,000, that just means 2,000 or more. So what we're going to put here is we're going to put 9E999. Yes, I recognize you can't have an infinite test score, but that's what we're going to put in. Now guys, pause for a minute and pause the video if you need to think about this. If I hit enter right now, I'm going to get a ridiculous answer because there's something that I have not thought about or mentioned. So pause the video, see if you can figure out what that is. So what I've forgotten to use is my mean and standard deviation up here. So I need to come back and change that before I continue. So mean 1509, oh, mistake 1509, and I need to put in my standard deviation of 312. Because remember, your calculator doesn't know the context unless you give it all the information. So look at that. It looks like 5.7%, so I make that a question. It looks like 5.78% of students will get that score higher. And so that's why colleges like this, because it's not just that you're getting a score. Your score tells colleges what percentile you're in against all the other people that are wanting to go to college in the country. So that's the idea of this. And it's not necessarily perfectly useful in comparing you against people from other years, because what they do is they call normalizing the scores. They scale them so they fit this curve. And that's what a score of 2,000 means. It means that you're in the top 5.78% of all students. And that's why it's useful to the colleges. Now let's take a look at something called a Z-score, okay? And what a Z-score is it was really, really useful back in the day before we had TI Inspires. Now with normal CDF, you plug in the bounds and it spits out your area or your probability, and we feel really good about that, and it's easy. We used to have to look at a table of values like this one. And in order to do that, we'd have to first calculate a z-score. This little guy right here is actually z. And we'd find our z-score, and then we'd figure out what our area was, and oftentimes we'd have to do a little bit more legwork than that, and then finally, eventually, we'd be good. Now, even though we have TI and Spires, once in a while, we will see a question on an IB exam where they still use this even though it's not necessary, and they'll expect you to know what it is. So let's annotate it really quickly so you'll, at least in your notes, know what it is in case you ever need to use it. We already know that mu is the mean. And we already know that sigma is the standard deviation. And this is our x value in context. So, for example, if we want to know how many students scored more than 1,700 on their SAT, that number would be 1,700. And what z is, that's called a normalized, well, it's a z-score or a normalized z-score. What it does is it finds the x value that relates to all these factors on the standard normal curve. Okay, my R's look like V's, and my V's look like R's, and they all look the same. All right, so it's on the standard normal curve. So what that means is essentially this table applies perfectly to the standard normal distribution. However, when you get a question like we saw with the SAT scores, we have a different mean and a different standard deviation, and so we'd need a different table. But what people recognized early on is that this is still the same bell curve. It just had a couple of transformations that were applied to it to get it to be out here where the mean is now 1,509. So the way you do that is you'd take a bell curve, standard normal curve, with 0 right there, and you would shift that to the right 1,509 units. And you got to think back what we learned last year about transformations. Because what we would do is we would just subtract from the value, and that would shift it to the right. Okay, so that right there, shifting it to the right. This right here, the standard deviation tells us how spread out our data are. So dividing by the standard deviation will stretch or shrink the bell curve so it fits our actual context. And so this is just undoing that to get back from our context back to the standardized score so we could use the table. It's unusual that this pops up on an IB exam, but it could happen. And this formula is in the formula book, so it's important that we've annotated it and at least know what this stuff is. One more new command to learn about, then we'll practice, and then we'll be done for the day. Okay, so this one is the inverse norm. Now, many of you probably realized when we were going through our buttons in here that there is also something called the inverse normal. Okay, we're not using the PDF. We already know how to use the CDF. We're going to talk about the normal. Okay, so the inverse normal is simply this. It switches the inputs and outputs. So your input will be an area, and your output will be an x value. So you may wish to write that down. I'm going to show you an example here. So let's say that I wanted to know the answer to a question like this. I would like to know 75% of testers score higher than what score? So that's what I mean. Your input is a percentage or a probability or an area. It's the opposite of what we did before. And then your output is going to be an x value. It's going to be somewhere along this x-axis. So let's look at how to input that. So let's click on inverse normal. And it says, hey, it's an area. Now, I have to think about how I'm going to pick that area. I can't just automatically take whatever they said and put it in. 75% score higher than blank. Okay, prediction number 1. Do you think that score is going to be higher or lower than the mean? Since more than half the people are getting that, it's going to be down here somewhere, which tells us this area is 0.75. Literally, 0.75 is higher than or greater than what that score is, which means that down here is the other 25% of the people. Or I shouldn't put percent, but I'm going to say 0.25, so scribble that out. Okay, 0.25. And so the way the calculator works, when you give an input like this and you say area, it's going to start shading the graph. And it's going to stop shading when that area or when that integral that it's shaded has reached a total area of whatever you put in. So if you put in 0.25, it's going to stop right here, which is exactly what we wanted. If you put in 0.75, it's going to keep shading. And here it's going to get to 50% right in the middle. So at the middle, 50%. And it's going to keep shading, and it's going to end up somewhere over here. So you're going to get this number. The calculator's not going to tell you that it's wrong. So we need to realize that what we're going to use as our input, once we draw the picture, we're always going to use the area to the left of our x value of interest. So I know it's a little weird, but we're actually going to put in 0.25 right here to answer this question. Don't put in 25. Remember, the greatest value you can put in there is 1 because the area under the normal curve is 1. So we're going to put in 1509, and we're going to put in 312, and we're going to see what we get. Okay, 1,298. So 75% of testers score higher than 1,290. And actually, I'm going to round to the nearest whole, so 1,299. I don't think they give out partial scores like that, or non-integer scores, I should say. Okay, so that's how we answer a question like that. Now from here, I want to use the rest of our time today to look at example questions of what we would be expected to do, either on my exam or on a final exam or an IB exam. The lifetime of a battery follows a normal distribution with a mean of 40, standard deviation of 0.9. We want to know the probability that a randomly selected battery goes for more than 42 hours. I like to draw a picture for these. It really helps me understand what's going on and what I'm after. So what I like to do first, I'll put the mean on here. The mean is 40, and we are interested in 42 hours. So I'm going to put a 42 on there, and we're interested in more than. So I'm going to shade to the right of that. And instantly that helps me see what I need to input on my calculator. So that helps me get right into here, 552, because it's a CDF. I'm not starting at negative infinity. I'm actually starting at 42. So I'm going to put my 42, and then my upper bound, I'm going to go to infinity on that. And in the context, no, the battery's not going to go infinitely. But remember, the calculator doesn't understand the context because we don't have a way of inputting that. And it thinks the normal distribution goes on forever to the right. So that's what we're going to put in. We're going to satisfy the calculator with that. 42 for our mean, or excuse me, 40 for our mean, and 0.9 for our standard deviation. And off we go. 0.0313. Not very likely. 0.13. And notice I'm not going to write a percentage. It's really tempting. I know we understand percentages, but it asks for a probability, so I'm going to give exactly what I was asked for. That's how I get all my points. Let's go to example 2. All right, now we're dealing with a Boeing 747. It's going to burn 3,213 gallons per hour, and we've got consumption normally distributed. Nice. They told us that it's normally distributed, and standard deviation is 180. I'm going to label these questions 1, 2, 3, 4. What I'd like to encourage you to do is to pause the video and figure out if these are CDF or PDF questions. Even if you don't have an Inspire, that would be a way you could still engage in the learning right now. So when you're ready, hit play. Okay, the first one is going to be a CDF because I have bounds. And so I'll plug in my bounds of 3,000 and 3,500. Don't forget to plug in your mean and your standard deviation. And then life is good. Okay, so 0.826. Okay, what about the next one? Going to consume less than 3,000. Okay, guys, some of you can look at this and figure out what the bounds are going to be. For some of us, it's more confusing, though. If you're confused, draw the picture. Less than 3,000. 3,000 less than. Okay, and I hope that helps you see the lower bound is going to be negative infinity. So I'm going to go up here, grab this guy, pull it down. So now our upper bound is 3,000. Oops. It's 3,000. Lower bound, negative infinity. And we get 0.118. So not very likely. Okay, what about more than 4,000 per hour? Hey, I can actually shade the same thing right here. So 4,000. Now we're shading to the right, so that helps me see my bounds. My bounds are going to be, for my lower, I'm starting at 4,000. And my upper, I'm going to go infinity. And no, we're not going to burn infinitely many gallons per hour. However, again, the calculator doesn't know the context. So that looks like a good setup to me. And whoa, what the heck is that? Hey, y'all, that's actually 0. So if we take 0.000, we're only taking those first 3 digits. That rounds to 0. So what's that saying? We're not going to burn more than 4,000 per hour. Even if we did, that'd be bad. The plane's going to run out of gas and it's at a risk of crashing. So a situation like that would not be okay. And maybe that's why that's excluded from here, but we're not going to burn that much. Okay, and this last one, notice the difference. We're given a percentage. 15% of the time, we're going to burn more than blank gallons per hour. So what they're trying to tell us is this is an inverse norm question. All right, and notice how quickly I'm getting to those buttons. Once you practice this, you'll learn the keystrokes that get you to this dialog box. That can save you a lot of time on an exam, which is a good thing. So I'm going to draw a picture on this one even so. It doesn't take me very long to do. It's not very costly in terms of time. 15% we burn more than, so 15% is on the more than side. We burn more than some amount, which means I have a 0.85 over here. Which one am I going to be plugging in for my area? Always the one on the left. So 0.85 goes in here. We'll plug in my other inputs. And off we go. So it looks like that rounds to 3,400 gallons per hour. Okay, and that's that. One more. Okay, this one's about soda bottles or pop bottles and those big 2-liter bottles. So with these, this question is predicated on the idea that when you look at two soda bottles, they don't have the exact same amount of liquid in them. There's a little slight variation from the manufacturing. I don't know if you've ever noticed that, but next time you see a bunch of those bottles in the store, look at them. You'll actually notice this. This is something that actually happens. If the bottles are too full, they won't ship them. We'll get to that in part B in just a second. I'm going to call this 1 and 2. All right, so this question is going to be about 2-liter pop bottles in the store, and what it's predicated on is the fact that when you look at the 2-liter bottles, they don't all have the exact same amount of liquid in it. You say, but wait, they're 2 liters. Yes, that's the bottle size, and they aim to have them be exactly 2 liters or 2,000 milliliters, but they're not always exact. So look for that next time you go in if you've never noticed that. There actually is a slight difference. So let's try to answer these questions then. What's the probability that any given bottle has less than 1,994 milliliters? For me, I'm going right to my CDF on this. And I can draw a little sketch. Now, I'm not going to grade you on these sketches, but if they help you, you should be drawing them. I mean, for me, like when I first learned this, I always drew these, and it gave me a lot of confidence in what my calculator inputs were. So less than 1994, less than is to the left. Okay, so I can see negative infinity is my lower bound, 1,994 is my upper bound, and then I'm going to put in my mean and standard deviation. Cool. So there I can see the probability of that happening is less than half, 0.30. Looks like it's 309 actually. Okay. Second question, 7% of the bottles are too full to be shipped out. All right, they gave me a percentage. That's a hint. Okay, so menu 553 for inverse norm. It's like a phone number, menu 553. So we plug that in, and I'm going to draw this one again because these were the ones that always confused me when I first learned them. Okay, so 70% of the bottles are too full. Notice too full means it's to the right on this graph or to the left? Probably to the right. So down here we have 0.07, okay, and which means on the other side of that our complement is 0.93. And remember, we're always using the number on the left. So 0.93, the area on the left of our x value of interest. So 0.93, don't forget your mean and standard deviation. And off you go. Okay, and once you get good at these, it'll be pretty quick. I'm going to round that to the nearest whole, 2018 milliliters. If they fill them any more full, my guess is that more than likely, because they don't have that little air bubble in them, anytime you dropped them, they just shatter because there's nowhere for the pressure to go. And so you'd just be breaking bottles left and right. With that little bit of air bubble, use a little bit of a cushion so you can shake them or drop them and they don't explode right away, which is kind of a nice feature if you're shipping bottles that they don't break all over the place. Final question. I'm going to call that question 3. We call that 1 and 2. How do you tell when it's CDF or inverse? And this is just a concept question. I would never quiz you on this, but I want you to be able to understand it because I think this will help you get through your applications. So think about what the inputs and the outputs are for each of those functions. Okay, for CDF, your input is bounds. So if you know the bounds, like less than 1994, there you go. What's going to come out? A probability, or an area, or a percentage. What about inverse normal? What was our input? It's usually a percentage. But it can be a probability, and it can be an area. Hey, notice, those two are the same. That's what an inverse does, by the way. It switches the inputs and outputs, so that actually makes sense. And what are the outputs? Bounds? Okay, it doesn't really give us bounds. So notice over here on our calculator, it's giving us an x value in our context, which is kind of like a single bound, but that's why we have to be careful about which version we choose for our array. You got to choose the one on the left. That gives you an x value in the context. Okay, so that's all for today. Hope you enjoyed the video, and we'll see you next time.